All right, we're diving into some seriously wild territory today with this paper, attempting to build our universe from the ground up using quantum mechanics.
Yeah, it's a fascinating idea. Big implications if it holds up. Could our reality really be a consequence of quantum processes?
Right. The paper starts off talking about these quantum harmonic oscillators, so I'm picturing like tiny little springs all vibrating.
You got it. Think of a guitar string vibrating. That's your classic harmonic oscillator. But in the quantum world, those vibrations, they can only happen at specific energy levels. They're quantized.
So it's not just any random vibration, it's like specific notes those oscillators can hit.
Exactly. And that's where it gets really interesting. The paper uses these mathematical things called ladder operators. They describe how those oscillators jump between those energy levels.
Ladder operators. Okay, getting a little technical now, but this is where they start connecting these oscillators to space and time itself,
Yeah,
right?
you're catching on.
Yeah.
Instead of just saying space and time are pre-existing, they're using the math behind these oscillators to build something called spinors.
Spinors. Okay, now we're really going down the rabbit hole. What are spinors and what do they have to do with anything?
Basically, they're these mathematical objects, and they have this weird property where they change their sign when you rotate them 360 degrees.
Wait, so they're like double-sided arrows or something?
Yeah, you can kind of think of it that way. What makes them so important is that this property makes them perfect for describing things like angular momentum, and for this paper, the very structure of space-time.
Hold on, hold on. We're going from tiny vibrating springs to the universe's underlying structure here. How do we get from point A to point B?
That's the real beauty of this paper, and where we'll see how these really abstract mathematical things might actually be the building blocks of our reality.
Okay, so we've got these spinors, these double-sided arrows, somehow making up space and time. But how do we go from, like, arrows on a chalkboard to stars and planets? You know, the actual universe.
Well, that's the big question, right? And this paper gives us a really interesting way to think about that. Basically, it all comes down to how these binaries interact with each other.
Okay, so walk me through this. How do interactions between, like, mathematical objects, even if they're super weird ones, create something that looks like the universe we see around us?
So picture each spinor carrying information. Information about space-time, like which way it's oriented, how much it's curved, all encoded in its math. When they interact, all that information is shared and combined. And the paper's equations, they show that this naturally leads to a 4D space. And get this, it has properties that look a lot like our space-time.
So it's like these spinors are, what, weaving together the fabric of reality, each interaction adding a little thread to the universe's tapestry or something.
That's a great way to put it. And it gets even cooler. They don't just stop at, hey, the math looks like space-time. They take it a step further and connect this whole thing to, you ready for it? Quantum entanglement.
Entanglement, that spooky action at a distance stuff. Didn't expect that to pop up in our universe building project.
It's a big deal here. See, the paper suggests that it's actually the entanglement between these spinors that's holding the fabric of space-time together.
Let me see if I've got this straight. Are we saying that space and time, as we know them, might just be the result of all these tiny quantum interactions? Like entanglement happening on a scale we can't even wrap our heads around?
You got it. What we see is smooth, continuous space-time. It could all just be an illusion. It might actually be emerging from a web of entangled quantum things.
I gotta be honest, that really messes with how I usually think about, well, existing. But if this is true, wouldn't we have, like, seen some evidence of this quantum structure in the universe by now?
It's a great point, and that's where this paper acknowledges that it's still very theoretical.
So we've got this amazing idea, right? Space and time, the whole universe, maybe it's all just a bunch of tiny quantum interactions playing out. But how do we actually know if any of this is true?
You're hitting on the core issue here. It's a beautiful theory, really elegant math, but connecting that to the real universe, that's the challenge.
Exactly. For example, what about gravity? This whole paper seems to be working with a flat universe. And we know that's not how things work, right?
Right, and they actually address that in the paper as a limitation. They're focused on a simplified model of space-time,
Mm-hmm.
no gravity to make things messy. It's a starting point.
So they've got the fabric of the cosmos, but haven't quite figured out how to, like, get the wrinkles of gravity to form.
Exactly, and that's not a small detail to overlook. Gravity shapes everything we observe about the universe.
Mm.
You can't just ignore it if you want to describe reality.
Fair enough. But even still, it's incredible that they've linked these tiny quantum happenings to something as fundamental as space and time itself, right?
Oh, absolutely. This work is really exciting. It's like opening a door to a whole new room in physics, and we had no idea it was even there. It really makes you think about how much more is out there to discover.
It really does make you think, what does it all mean? If our universe isn't built on space and time as we know them, but on these quantum interactions, it kind of changes everything, right?
It's a profound question, and I don't think anyone has the answer just yet. It really throws into question everything we thought we knew about the nature of reality.
Either.
This paper doesn't have all the answers, but it definitely asks some very, very good questions.
So where do we go from here? What are the next steps for this whole mind-blowing concept?
Well, the paper actually points to some interesting future research. One of the biggest ones is figuring out how matter fits into this whole picture. They've got space-time emerging from quantum stuff, but what about the particles that make up, well, us and everything we see?
So they built the stage, but we don't know who the actors are yet, or what play they're putting on.
Great analogy. And figuring out that next part, how matter interacts with this emergent space-time, that could be huge. It might even lead us to a unified theory of quantum gravity, which has been the holy grail for physicists for decades.
Wow. So this paper, even if it's just a first step, it could be the start of a whole new chapter in physics.
I think it has the potential to be truly revolutionary. It's really pushing the limits of our understanding and forcing us to re-examine the most fundamental aspects of our universe.
Well, I think that's a pretty good place to leave it for today. We've gone from tiny oscillators to the fabric of the universe and everything in between. And who knows, maybe this paper will be the spark that ignites a whole new understanding of the cosmos. This has been The Deep Dive, reminding you to never stop questioning and keep exploring the universe and all its wonders. Until next time.